graph terminology and other special types of graphs. This section is going to be mostly about the terminology used in graph theory. We'll talk a little bit about the special types, but mostly about just terminology. First up, let me go ahead and get a graph here so we could talk about it. The same one we talked about previously with A, B, C, and D connected in this manner by edges E1 and E2. So we've got a basic graph here, and let's see. First vocabulary word we've got is neighbors. Okay. Vertices that are connected by a given or an edge are considered neighbors. So vertices connected by an edge. That's all there is to it. Okay? In other words, vertices that are right next to one another are considered neighbors. Also, they are said to be in incident with each other. These vertices are said to be in incident or incident with the edge. So incident with is another little vocabulary word, but that's only used sparingly. Oftentimes we'll just refer to these as neighbors. Then the neighborhood oh, I misspelled neighbors. Or did I? Nope. Beginning to misspell it. Neighborhood of a vertex V is the set of all vertices who are neighbors to V. Denoted N of V. So, as an example, the X-Men looking symbol, again, means, or my notation for example. As an example, in this graph over here, the neighborhood of A is the set containing vertices B and C. And we say the degree of A is 2. Degree of A meaning the number of connections to A, not the number of neighbors. Because our graph is a simple graph, we can say that this is the case, that the degree of a vertex is equal to the number of neighbors, only because it's simple. But more specifically, the degree of a vertex is the number of edges connected to it. Here we have one edge here and one edge here that are connected to A. It is possible to have a graph with a loop in it, like this. In which I have, let's say, O, E, F, and H. In which I have 3 edges as well as 3 vertices. And this loop is going to count twice. So this is 1 connection, 2 connection. You can think of zooming in on your vertex. In this case, if we were to zoom in on vertex E, looks kind of like this. We know that out here, these 2 ends of the edge will eventually connect, but at this point, if we were to zoom in, we can see that there are 1, 2, 3 connections leading to or coming from E, and thus the degree of our vertex E is 3. A couple other words that are used every now and then. An obvious one, isolated. An isolated vertex is one in which the degree is 0. There's no connections to it. It's all by itself. It's called isolated. And an isolated vertex will have degree 0, kind of like D up there. Okay. Another word which kind of makes sense if you look at it in the right light is pendant, which is probably going to be misspelled. But a pendant is a vertex with degree 1. So we've got an isolated vertex and a pendant vertex for, let's say, the graph G equals VE. So again, set of all vertices in the graph and set of all edges in the graph. For this graph, the neighborhood of some set A is just going to be the union of all the neighborhoods of vertices for each vertex in the set A, where A is some subset of V. Okay. Of course, the neighborhood of big V itself would be the entire set of vertices. It would be big V. Go ahead and write that down. Neighborhood of big V. Again, that's big V, not little v. Neighborhood of big V is simply big V. Right? Neighborhood is a set of vertices. So this is not, and a common mistake is to write graph. This is not the graph itself. The neighborhood is a set of vertices. The edges do not come into play when we're discussing neighborhoods. Okay. So, just showing that up from the last page. Now, a couple theorems from the text. Theorem 1. If G equals, so the same graph as above, and I'm going to stop writing this after a while because it's always going to be G equals VE. If we have this graph with M edges, so the number of edges is M, then we know that the sum of all the degrees for all vertices in V is simply 2M. So that's kind of a handy fact, a way to count the number of edges in terms of degrees. There's an obvious relationship between the degrees and the edges, but this just kind of shores things up for us. Also, Theorem 2, I've already discussed a directed graph, and you'll notice on the previous slide this was an undirected graph. So on that undirected graph, has an even number of vertices of odd degrees. An undirected graph has an even number of vertices of odd degree, which is also very handy when we start talking about proofs. So, quick example. Draw a similar graph to what we've been using. A, B, C, and D. I'll go ahead and throw a loop here on B. And we can double check that these theorems hold. Of course, there are 1, 2, 3 edges. So from theorem 1, m equals 3. And the degree of A plus that of B plus that of C plus D, but D's 0, and I'm running out of space. So if we add these degrees together, the degree of A, if we zoom in here on A, or look inside this circle, we can see there's 1, 2 connections to A, so the degree of A is 2. If we zoom in here around B, again looking inside that circle, inside the circle I have 1, 2, 3 connections there, and the degree of C, again zooming in on C, I see there is a single connection. Adding these together, of course, we get 6, which is 2 times 3. So theorem 1 checks out, and it's a little more difficult to prove. I believe the proof might be in your text. If not, I know you can find it online. But for theorem 2, if you just look at your graph and draw a few pictures of graphs, looking at them close, this should be pretty clear. But what's exciting about this is that it works for all possible graphs. For any undirected graph, this property holds. And that is that the graph has an even number of vertices of odd degree. Okay, odd degree vertices, that's going to be here and here. So in this case, well, here we've got a degree of 0, here we've got a degree of 2. So only 2 vertices of odd degree, that's an even number. So theorem 2 checks out as well. Now, directed graphs. Just a little bit more about them. Basically, we just talked about some vocabulary words with undirected graphs. Now we're going to discuss those same or similar vocabulary words for directed graphs. With the directed graph, of course, the only thing that changes is we put some arrows on the end of each of those edges. So instead of just having the connection from A to B and A to C, and then there's the loop from earlier. Now I'm going to have directions associated with each of these. Okay. So each edge, and there's 1, 2, 3 edges, has a direction. 1, 2, 3 arrows talking about its direction, or each edge's direction. With directed graphs, we can discuss initial and terminal vertices. Okay. The vertex that it begins at and the vertex that the edge ends at. Of course, if the initial vertex equals the terminal vertex, that means the edge is a loop. So that could be helpful as well. If the initial and terminal vertices are the same, of course, that means that it begins and ends at the same vertex and is thus a loop. We're not talking about a path here, so we're not talking about it going through multiple vertices, just a single vertex right now. So, in addition to in and out, initial and terminal vertices, we can discuss the in degree of a vertex, V. The in degree is going to be denoted with a superscript minus sign or negative symbol, and that's the in degree of a vertex, meaning the number of edges for which V is a terminal vertex. The number of edges for which there is a directed edge, or sorry, the number of times for which a vertex has an edge going into it. Number of times this vertex has an edge going into it is the in degree. Okay, so this is number of edges for which V is a terminal vertex. And of course the out degree will be similar, denoted as you would expect with the superscript plus. That's going to be the number of edges dot 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 for which V is an initial vertex. Number of edges for which V is an initial vertex. Now it's not as easy as simply adding up or zooming in on some vertex. You can still think of it that way, but we've got two additional types of degrees to discuss. So theorem 3 takes that into account. And that is the sum for all V's in our vector space. Vector space, it works. Of all in degrees should be equal to the sum for all V in the vector space of out degrees. And both of these are equal to cardinality of the set E, which of course is the number of edges. Whoops. In the graph. Right. If each edge in a directed graph can only have one initial point and one terminal point, then we can count them by just counting all of the terminal points or all of the initial points, and that should give us the number of edges in the graph. Okay. Also, with this we could discuss the underlying undirected graph. The underlying undirected graph of a graph G that might be directed is simply well, you can obtain simply by taking away all of the directions. So just erasing the arrows, literally, is all it takes to come up with an undirected graph. We can verify that Theorem 3 works looking at this graph pretty quickly. Quick note, as for the underlying undirected graph, remember that all that matters with these graphs is the relationship, not the exact placing of each of these vertices. So in this case, the underlying undirected graph, again, just taking away each of those arrows, would look like this. Now for a couple special types of graphs. I'm not going to list all of them that are in the text, but the definitions are quite similar. The most interesting special graph, and the most, you can't really say the most common, but just about the most used as far as examples are concerned, is the complete graph. A complete graph is one in which there is an edge between every pair of vertices. An edge between every pair of vertices. So, complete graphs, if we have, say, 3 vertices, are really simple. A complete graph with 4 vertices, again, pretty straightforward. Where it gets complicated is where we add vertices, of course. So there's 4 vertices, a complete graph, 5 vertices. Oftentimes you'll see these arranged as regular polygons. And we just need to connect every vertex to every other vertex. Like that. Oh. Like that. These are often denoted as case of n. In other words, this is the complete graph with n vertices. We could say that, we could say that the cardinality of V, the set of all vertices, is n. And if we look at some of these examples over here, the sum from k equals 1 to n, that's little k, sorry for the notation, from k equals 1 to n minus 1, if we add up each of those numbers, of course that's going to be n times n minus 1 over 2, then we can get the number of edges. Okay, so looking at this kind of helps to go ahead and draw or fill in a graph of 5 vertices. We can start by connecting, so we start here in this corner, and I could draw 4 edges here. Then I move to this corner, and I've already got an edge linking those 2 vertices, so I can only draw 3 more. Then continuing around, I've already got 2, so I can only draw 2 more. And finally I can only draw an additional 1. So I start with 4, edges that I could draw, then 3, then 2, then 1, adding the numbers from 1 to 1 less than the total number of edges, 4. Or sorry, total number of vertices, which is 4. And we end up with, what is that, 6 plus 4, we end up with 10 for the total number of edges. Another special type of graph is the I'm going to mispronounce it probably, but bipartite graph. Bipartite graphs have some interesting properties. And we say that G is the graph with vertex set V, edge set E, is bipartite if V can be partitioned into two different sets. Say V1 and V2, where edges connect only vertices in V1 to vertices in V2. Not V1 to V1, oops, nor V2 to V2. Only V1, between V1 and V2. We call the ordered pair of V1, V2 the bipartition of V of G. Bipartition. Okay, so an example of a bipartite graph would be something simple like this. This is an example of a bipartite graph, because if V equals A, B, C, and D, the set containing those vertices, then I could partition it. Remember, partition means that the two sets, V1 and V2, are mutually exclusive, have no common elements, and that if we take the union of V1 and V2, we will get the entire set V. That's what a partition means. So, if we look at this, how can we partition the set V so that we have two sets which connect only between the two, V1 and V2, not V1 to V1 nor V2 to V2. Common mistake is to go ahead and say these two vertices are one partition and these two vertices are another. Again, that's a common mistake, but notice that if we take only A and C and then B and D together, those are the negation, if you will, of what we want. We want to connect V1 to V2, not V1 to V1 and V2 to V2. So the correct partition would be to group these two vertices and these two vertices. Okay. If we do so, then we see that V1 is the set containing A and B, V2, and of course arbitrarily named, is the set containing C and D. And here A connects to C, something in V2, B in V1 connects to D, something in V2. There could be much more complicated graphs, of course, that are bipartite, but It's always good to have a simple example in your head when you're reading things about these bipartite graphs. Theorem 4 goes a little bit more in depth with this. That is, simple graph is bipartite. G, simple, is bipartite if and only if it is possible to assign one of two different colors. One of two different colors to each vertex, so no two adjacent vertices are assigned the same color. So that no two adjacent vertices have the same color. Adjacent, of course, meaning neighbors. Direct neighbors, if you will. A set like this one. We'll just stick with the 4 elements because it's simple enough. Question is this set bipartite or is it not bipartite? If we start to color some vertices, we can check the fact that it's bipartite by go ahead and coloring that one red. If that one's red, then this one must be green because it's a neighbor, which means because this one is an incident with this edge, common edge, that one must be red, and finally, this one must be green. Okay. So there exists a coloring in which, using two different colors, each vertex has a different color from an adjacent vertex, or a vertex that is near the other one. So if we look at these two versus these two, we could check and make sure it's bipartite. This vertex only connects to this vertex, which are in different partitions. This vertex only connects to this one and to this one. Again, vertices in different partitions, and the same going across here. So indeed, this is bipartite. Matchings. A matching M is a subset of E where no two edges are incident with the same vertex. The associated vertices of that matching M are said to be matched in M. So, if we take a subset of E, the set of all edges, if we take a bunch of edges with the property that no two of them are incident with the same vertex, then we have a matching on E. Simple matching. Let's see, A, B, C, and D. Something like this. Well, we can even throw this in there. Okay. Here we have a matching. Well, here we have a simple graph. And if we take, label these E1, 2, and 3. If we take M to be the set containing E1 and E3, then we have a matching. And BD as well as AC are matched by this matching. Okay. So we're just showing that we've got this relationship. Okay. Not too difficult. Excuse me. If M is on a bipartite graph, with bipartition V1 V2, then M is the complete matching of, well, from V1 to V2. For example, this graph, which we've seen earlier, has V1 up here and V2 down here. With matching of these two edges. Then M, the set containing these two edges, is the complete matching from V1 to V2. A good application of matching is in marriages. Obviously not assuming polygamy. We're assuming that one person can be married to one other person, thereby separating the two separating or partitioning v1 and v2, your set of all vectors, into two different sets, spouses of other spouses. Theorem 5. The bipartite graph G with vertices V, edges in E, and bipartition V1, V2 has a complete matching from V1 to V2 if and only if the number of elements in the neighborhood of some set A is greater than or equal to the number of elements in A for all subsets A of V1. That is, A is a subset V1. Okay. Of course, V2 could be used as well, but we don't need for both V1 and V2 to be true. We only need for one of them to be true. I believe, not confident, but I believe if one is true, then so too will the other one. So we need for this to be true in order for us to have a complete matching. Let's check that one of our previous examples is in fact a complete matching. A, B, C, and D. And let's use this graph here, in which we have E1, 2, and 3. Then we've got matchings, Then we have a matching of O, I guess the only possible one is E2, comma, E3, which matches A, matches A to D and C to B. So we have, excuse me, A to D and C to B. So we have partition, let's say V1 is the set containing A and B, and V2 is the set containing C and D. Okay. Now, that's a subset, or a possible subset of V1. We have the set A, set containing A, is a subset of V1. Set containing B is a subset of V1. And the set containing A and B is a subset of V1. The set of all, neighbors of A is the set containing See, A is connected to D, and A is connected to C. So, C and D. And it has cardinality 2. Set of all neighbors of B. It's just the set containing C. B is only connected to C. So, cardinality 1. The set containing A and B has neighbors of a little lax on my notation there, but get the gist. Set containing A and B has neighbors of D and C. Notice A and B are not neighbors of one another. So it has cardinality 2. Now, we could verify that this is in fact the case for all subsets of V1. Cardinality of the neighbors of A is 2. And the cardinality of that set is 1. So 2 is greater than or equal to 1. Works there. Here we have cardinality 1. That is in fact greater than or equal to 1. Check. And here we have 2 members in that set, A and B. Oh, sorry. Yeah, 2 members in the set A, B. Cardinality of this set is 2. Cardinality of the set of all neighbors is 2 as well. Thus, that one checks out as well. So, as it should, if we call this G, G has a complete matching from V1 to V2. Note, this does not give us a complete matching. Nor does it say that the matching that we found is the complete matching. All it says is that there is a complete matching from V1 to V2. Now, quick example. Here we've got a graph G. We can go ahead and denote G to be the graph, vertex set V and edge set E, where I just labeled all the vertices and all the edges. Okay. The book, the definition may be a little wordy, I guess would be how I'd describe it. It's very, very simple when you talk about a subgraph of a graph. First of all, a subgraph has, in this case, call this subgraph W, and let it be a graph with vertex set H and edge set F. Okay. F is a subgraph of G. It's a proper subgraph because it is not equal to G, but a subgraph nonetheless. And it's a subgraph because H is a subset of V, and F, the set of edges that you see here, is a subset of E. Thus, W is a subset of G, the top graph. When the book mentions a subgraph induced by a set, here I've got a subgraph induced by this set H. Okay. H is a subset of V. The only thing remaining to do here is figure out which edges are members of the subgraph induced by H. The edges that we include are only edges with a terminal and initial point, or only edges that connect to two vertices within that set. In other words, you'll notice up here we have E2. E2 is not included in our subgraph because E2 is connected to B. Okay, so all you have to do is go up to your original graph. If you want to, circle those letters that are in the inducing set, and then go ahead and draw in any edges that connect any of those vertices. And that's all there is to it. So not too complicated at all. If we want to go ahead and write this out, let's see, E6, then F would be the set containing E3, E5, and E6. So it's a subgraph induced on the set H here. Now, wanted to go ahead and use this graph as another example to discuss whether or not, for example, this one is a bipartite graph. Okay. So, question is graph G bipartite? Give you a second to go ahead and look at it yourself. Now, I'm going to go ahead and draw theorem 4 into play, which states, if you'll recall, that if G is simple, it is bipartite if and only if it is possible to assign one of two different colors to each vertex so that no two adjacent vertices have the same color. So, all we have to do is take two colors. I'll take green and red, as we've done before. Pick a place to start. It doesn't really matter where we start. But if, let's say I start with B, I'm going to color this vertex green. Then anything attached to that vertex through some edge must be colored red. So C must be colored red and A must be colored red. Okay? If we cannot complete this in this manner, then it's not bipartite. So we've got the red ones here, and connected to this red one, I've got this vertex, so that must be green, and I've got this vertex, so that must be green as well. Also connected to this red one, I've got this vertex, so that must be a green vertex. Now, I've shown that I can in fact color this graph so that no two adjacent vertices have the same color. None of these edges connect vertices that are both red or both green. So this is a bipartite graph. G is bipartite. Now, so we found that it's bipartite. Now what? Now we can go ahead and partition it. We said it's bipartite. The partition is going to be the two sets that we can separate it into. Well, by coloring it, we've already separated it into the two different sets. Here, I've got my red set and my green set, so I can call V1 set containing A and C, and V2 the set containing B, D, E, and F. So there's my partition. Where we go from there is we want to figure out if there exists a complete matching within this set. Okay. Again, the question I now have is, does there exist a complete matching between V1 and V2, or from V1 to V2? Does a complete matching exist? Now, to determine that, let's see, our theorem 5 stated that a complete matching exists in a bipartite graph if and only if the cardinality of the set of all neighbors is greater than or equal to the cardinality of that set for all subsets of V1. Okay. We need to verify that this is true. First off, notice that I conveniently labeled the smaller set as V1 and the larger one as V2. Right? Obviously that won't always occur, but if it's not the case, then you just label them differently. There's nothing saying that this one has to be V2, this one has to be V1. We could switch those labels, the 1 and the 2, very, very easily, and it wouldn't affect anything. So, this theorem 5 could easily read, without loss of generality, suppose blah 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 subsets of V1. Okay? It doesn't have to be V1 necessarily, just pick the smaller of the two. So you have to check less subsets. First of all, I'm going to go ahead and write down each of the subsets. Of course, the empty set's another subset, but that doesn't amount to anything. No pun intended. So, we've got these two sets. Now I need to check the cardinality of the set of all neighbors and the cardinality of the set itself. The cardinality of the set itself, well, that's pretty simple. The cardinality of the set of all neighbors of A. Well, the set of all neighbors of A, it's got 1, 2, 3 neighbors. All the neighbors of C, well, it's connected to 1, 2, 3, 4 other sets. Indeed, greater than or equal to, we've got greater than or equal to for both of those. Now, A and C combined, we've got A has F, E, and B. C is connected to everything else. So, cardinality of the set of all neighbors of A and C is 4 as well. 4 is greater than or equal to 2. Thus, there does exist a matching. A complete matching, sorry. Between V1 and V2. So, now the question becomes, what is that complete matching? Well, to find the complete matching, we need to look back at the definition of matching real quick. And a matching of a subset, is a subset of the edges where no two edges are incident with the same vertex. Okay, if we look back at some simpler examples as well, go ahead and throw down the very last slide here. If I look at this simpler example, I've got a matching here, E3 and E2. Well, that's pretty plain to see the way everything has been laid out here. I've got one partition at the bottom, one partition at the top, and E2 goes across the partitions, E3 goes across the partitions, neither of which contain the same vertex. So the idea is we need to cross the partition somehow. Looking back at ours, it's a little bit more difficult to see how we can cross the partitions. There's several different options here, but one such option for M, which is a complete matching, is E1 and E5. This is one of several possibilities for a complete matching. Again, this is a complete matching on the set, despite the fact that not all of our V2 members have found a matched pair. we have matched everything in V1 to something in V2. Again, it does not have to include every member of both sets, because there is a possibility of the sets being in different sizes. But we just need to match everything in V1 to something in V2 in order for that to be a complete matching. Here we do in fact have a complete matching.